Hello. This lecture will cover pages 215 through 218 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 12J, Bode Plot, Example 6. We're going to continue on page 215. We're going to show you how to handle the single, in this case, poles at the origin. Example number 5 showed you how to handle the single zeros at the origin, and now we're going to look at those single s terms in the denominator. Here's a transfer function t of s, my input and my output. I'm giving you the transfer function is 12 over s times the quantity s plus 3. That's in a break frequency form, not a time constant form, so I'm going to take out the 3, divide by 3, and when I clean this up, I'm going to get 4 over s times the quantity s over 3 plus 1. That's the transfer function we're going to start with right there. You have to be able to take the transfer function and get it into a form like that so we can extract, it's the time constant form we called it, but the break frequency is shown in the denominator here. Now, some of your homework problems, I'm going to give you a circuit. And you're going to have to use the circuit like we did in like example 2 and a couple other examples, previous examples, where you had to come up with the transfer function. And in some cases, I'm just going to give you the transfer function. But the reason I give you a circuit is it shows you the practicality of how you take a circuit and get to the transfer function, as opposed to just having a transfer function. So here's what we're starting with. Notice there's a single pole at the origin. That's a single pole because it's understood exponent's 1. So I take this transfer function and I start with k0 equal to 4. Right there it is. I can take 20 times the log of 4 and I get 12 dB, but that 12 dB isn't a constant 12 coming in. That's going to be, because I have a single s term, that's going to be the dB at 1 radian per second. We're going to use that as a check. At 12 dB, we should be at 12 dB at 1 radian per second when we finish this graph. So we'll come back and we'll check on that. What you're going to do when you see this transfer function here is you're going to get your k0, but we're going to use this in a minute. You're going to move right to omega 1. Your first break frequency is at 0. Right there it is. Radians per second. And it's a pole. It's in the denominator. It breaks down. Omega 2 is 3 radians per second. It's also a pole. It breaks down. Since the omega 1 is equal to 0, and we know that's DC, no frequency is DC, but the pole, since omega 1 is equal to 0, is a pole, the 0 dB intercept is given by this formula. We talked about that in the previous example, where n is equal to 1. N is equal to 1 up here. If n is equal to 2, we have to put a 2 in there. If this exponent is 3, I have to put a 3 in there. And I make a calculation using this formula. I get 4 radians per second. This is your starting point. This is your 0 dB intercept. At 4 radians per second, I'll be at 0 dB. But the difference is, this is a pole. It's breaking down. So it's not like the last example. It's not like the last example where we're coming in this direction. This example is a pole, so we're coming in attenuating the signal. We're at a negative slope, a negative 20 dB per decade coming in. So let's go to the Bode plot and see how we use this 4 radians per second. Well, what I did was I said 4 radians per second is going to be out here somewhere. I'm going to put it in the middle of the graph. Oops, I'm going to put it in the middle of the graph here at 4 radians per second. That makes this 1. That makes this 0.1. It makes this 0.01. And there's my 1, there's my 4 again at this point right here. That's going to make this 10 and 100. I label my omega axis that way. My 0 dB, I notice I'm breaking down. I'm going to be breaking down coming in. I have to get that line plotted. Right now you have a blank piece of paper. So I only have 1 point here. At 4 radians per second, I'm at 0 dB. I get a point right there. If you're real careful, you put a little dot on your paper, and I label that 0 dB. Well, on some of these graphs, you're going to get started on your own. I mean, I got you started through 6 examples, but some of them, you're going to see you're starting to plot, and you're getting off scale. So you're going to have to throw away the paper, and you're going to have to realize, well, my 0 dB axis should be here. If it was up here, you're going to have trouble. If it's way down here, you're probably going to have trouble at this end. So you get it figured out here, but notice I put my 0 dB axis here. In this case, I labeled this plus 40. So my plus 20 dB is right here. I'm not labeling it. Minus 40, minus 60, minus 80, minus 100, because I'm getting a double roll off out here, so I have to compress this a little bit. So here's my minus 20 dB. Here's my minus... Did I label that right? No, I didn't label that right. Doggone it. Yeah, I'm okay, though, because I didn't use these down here. Let me make this right here. This right here should be an 80. Make sure you change that on your paper. This should be 100. I don't even use this one down here. I'm not even going to worry about it. So there's my plus 40. There's my minus 40, my minus 80, my minus 100. I still did it wrong. That's 120. So my 0 dB intercept is at that point there. So what I do is I go back a decade from that 4 right here. I go back a decade from that 4 and I get my 0.4 and I label it. Okay, and at 0.4, if this is rolling down at minus 20 dB per decade, I have to go to 20 dB and put another at 20 dB here. At my 20 dB right there, I have to put a dot right there very carefully. And that's going to be at 0.4. And there's my 2 points. That's rolling off at 20 dB per decade. So I can put a dotted line in on your paper right through those 2 points. And that's all you have on your paper now is a dotted line that runs through here. That's that pull. That starts breaking way back at DC at 0 radians per second, which we can't show. You never get to DC, remember? So it just gives you a slope like that. Now, when you get to 3 radians per second, you have another pull that breaks down. So you never make it to this 4 here. I used that point here, and I used this point here to get a full decade so I can get my 0 dB up to plus 20 so I can get that line plotted accurately. Now I have to go back here to my 3 radians per second, which is this point right here, and that's when the pull breaks down again. So now I know that I'm coming down here until I get to this point here. I don't make it the whole way to this dot. This dot was just used to establish my breakdown. Remember that. The actual curve breaks again at 3 radians per second, which adds another pull. We had a pull on top of a pull. We don't have any cancelization here. We have a minus 20 dB per decade, and we go to minus 40 dB per decade here. Starting from this point at 3. So how do I establish this line? Well, there's my 3. I go out here a decade from 3. And I go to this point here, which is a 30. That's 1 decade up. And what I need to do, and I sort of messed up this line a little bit here. You're going to have to, hope you do a better job than I did. But I want to start here at this 3, and I want to go down from that point 1 decade, which takes it out to 30. So I'm on this line right here. Hard to see here, but I'm on this line. Let me draw it this way. I'm on this line right here, which is my 30. And I have to break down 40 dB because this is rolling off at 40 dB per decade. I have a double roll off at this point. So I want to get a point here at 30 and minus 40 at that point. That's the point I should have used. So I have a point here now, and I have a point there. So I draw my straight, this line goes away, and that line comes right down through here, which is a minus 40 dB per decade. This is a minus 1, shorthand notation, which is a minus 20 dB per decade. I hit my second pull here, which takes me to a minus 2, which is a minus 40 dB per decade. I just need 2 points along this line to get that roll off. I want you to notice it's a low pass filter. It's passing these lower frequencies, and it's killing the higher frequencies. But if we look back, we already knew that. if we look back in our example, I guess we didn't have the circuit. We didn't have the circuit in this case to look at it. So we don't have anything to compare it to. But that's my curve right there. Notice nothing was affected down here because I didn't use this minus 80 and minus 120. Just make sure you get that relabeled, or hope you labeled that correctly when you did it. But let me go back and check. If that curve is correct, a good indication is going to be that at 12 dB, 1 radian per second. At 1 radian per second, I should be at 12 dB. So I go back here to this curve and I look at my 1 radian per second. And if I go up and I take a look at that point right there, it's exactly, if you take a look here, it's exactly at 12 dB. And I did that. It is exactly 12 dB right there. What about our phase plot? What's our phase plot look like? Well, I lay out the omega axis the same way. I put 0 degrees here. I want plus 45. I want minus 45, minus 9, minus 135, minus 180. So I know my K0 term is always 0 degrees. That constant has 0 degrees here. I know my single pole is always going to be at minus 90, so I have a dashed line in here. So right now, if you're doing a Bode plot, you have a dashed line at 0 degrees, represents your K0 term. Okay, you have a dashed line going across at minus 90, which is that single pole, which is always minus 90 degrees. You know that by now. Single poles in the denominator is minus 90. If you have s squared, it's going to be a minus 180. If you have s to the third in the denominator, it's minus 270, but then you relay out this out here to accommodate everything. But what about that pole? What we know about the pole starts at 0 and goes to minus 90, and at the break frequency here, it has to be at minus 45. You know, poles break from 0 to minus 90 all the time of that form. And at the break frequency, you know it's at minus 45. So we just have to add those 3 dashed lines up. I think it's pretty easy to do. The constant's 0, so forget about that. Okay. Well, you don't forget about it. I mean, the influence, but the constant term you can forget about. But what's the base there? Well, the base is you always have this minus 90. So I know I'm always going to be at minus 90 because there's no contribution from either of these up until I hit this break frequency, up until I hit this point here, which is a decade down from the 3. A decade down from the 3, I'm at 0 because of this pole. A decade up from the 3, I'm at 0. I'm at minus 90 because of this pole of this form. So basically what's going to happen is this pole starts contributing to this minus 90, adding additional phase shift. So I know what this point is. This point's 135 because I have a minus 90 plus an additional minus 45, so I'm at 135 right here. So I know that's a valid point. I know my end point here is going to be a minus 180. So I can draw in my phase shift. Starting at minus 90, the pole starts to encourage the phase through minus 135, and I end up at minus 180. So there is my omega my phi with respect to omega. That's what the phase shift at the low frequencies, it's 90 degrees out of phase, input to output, and then at the higher frequencies, I'm a full 180 degrees out of phase. Well, let's check that. Let's go back and look at my original example here, which is 4 over s times the quantity s over 3 plus 1. Well, as s goes to infinity, as omega goes to infinity, j omega is s squared. But that s squared appears strictly in the denominator. It's 2 s's in the denominator. Both add 90 degrees, if you will. That's 180 degrees. But it's 180 degrees in the denominator. When you bring it to the top, it's going to be a minus 180 degrees. So at the higher frequencies, you're at minus 180 degrees. It's a good check. And then finally, we've done this on all the examples. Use the Bode plot to find the dB gain and the phase at 0.4 radians per second, and then use the Bode plots to find the dB gain and the phase at 50 radians per second. Then take a minute to calculate the actual values and compare them to the above readings that you got from the Bode plots. And you'll see they're very, very close, but they're only going to be as close as you take your time and accurately build these Bode plots. Now, we worked through 6 examples now, and we went through, wow, 6 different, averaging 8 to 20 minute, videos. So we're at about 2 hours worth of videos, just gone through the examples, the 6 examples that I've given you so far. Now, the next video, I'm not going to work them out. I'm just going to talk through examples 7, 8, 9, and you should be able to do those problems and be able to do the homework based on what I've given you so far. But that concludes this lecture.